Okay, so now let's do some exercises. First one, XS mu measure space 1 less than equal to P Q R less than infinity F such that one by P plus 1 by Q equal to 1 by R. If F is in LP mu and G in LQ mu, show that Fg belongs to LR of mu and that norm Fg in LR is listening to norm Fp, norm GQ. So this is just a generalization of the Helder inequality. So you have 1 by P plus 1 by Q equal to 1 by R. So this implies R is less than P and Q. And then you can write this as 1 by P by R plus 1 by Q by R equal to 1. And so P by R, Q by R will be greater or equal to 1. Okay, so then so we can apply Helder inequality integral x FGR d mu equals integral over x mod f to the r mod g power r d mu, and I'm going to apply Helder inequality with p by r and q by r. So this is less than equal to integral over x mod f to the r power p by r d mu whole power r by p, and then integral over x mod g power r to the q by r d mu whole to the r by q. That is the, you have to do 1 by p dash, so that's r by q. So now this is saying that which is equal to fr, this is just f power p, and then power 1 by p is norm fp to the r norm gq to the r. So this implies that fg belongs to lr mu, and you have norm fg r less than or equal to norm fp norm gq. To XS mu sigma finite measure space 1 less than P less than infinity. F from x cross x to R such that, so it's a mapping such that for every y in x we have Fy, that is the section Fy. So if you remember, Fyx definition is f of xy. Okay, Fy is p integrable, and integral over x norm of Fyp d mu y is less than plus infinity. Define g of x equals integral over x f of xy d mu y. Show that g is well defined. G is in LP mu and norm GP is less than or equal to integral over x norm f to the y p d. Okay, so solution. So we are going to use the duality method. So p dash conjugate exponent, just as we did in the case of convolution. So let H belong to LP dash mu. So let us take integral over x. We want to use Fubini's theorem. Mod f of xy mod gy h of x d mu y d mu of x. So this everything is non-negative, so you don't have to worry too much. So x integral over x mod fy of x mod hx d mu x d mu y. But that is less than or equal to integral over x norm fy p norm h p dash, okay, into d mu y, which is less than or equal to norm h p dash into integral x norm fy p d mu y. Okay, so this is finite. Therefore, by Fubini's theorem, for almost every x, you have integral hx f of xy d mu y well defined. So you take h in LP dash mu, okay, such that h is not identically 0, then you have that. So this implies that integral over x f of xy d mu y is well defined. Also h going to integral over x f of xy d mu y, sorry, h of x d mu y d mu x is a continuous linear functional on norm on LP dash mu with norm less than or equal to norm integral over x norm fy p d mu y. So this implies that integral over x f of xy d mu y equal to g of x belongs to LP of mu and g norm gp less than or equal to integral over x norm fyp d mu. So that completes the proof of this exercise. This exercise, this is sometimes called the Riemann-Lebesgue lemma. There are several versions of Riemann-Lebesgue lemma, so this is one such version. Okay, so h from 0 infinity to r, bounded measurable function, such that 1 by c integral 0 to c, integral 0 c h dm1 limit as c tends to infinity equal to 0. A. Let CD be contained in 0 infinity, f equal to chi of CD. Show that star limit omega tending to infinity, integral 0 infinity f of t h omega t dm1t equal to 0. Solution. So let us integral 0 infinity ft h of omega t dm1t equals integral over cd of h of omega t dm1t. That's equal to integral 0d of h of omega t dm1t minus integral 0c h of omega t dm1t. Now you can change the variable t going to omega t, and therefore this will become integral h. So it's a linear thing, the determinant is omega power n, this is a diagonal. Anyway, this is only one dimension, so you have this is 0 to omega t, omega d, sorry, h of s dm1s 1 over omega. Because omega dt is ds, so you have 1 over omega will come. Okay, and this will similarly this will be minus 1 over omega integral 0 to omega c of hfs dm1s. And then we know that this goes to 0 as omega tends to infinity by hypothesis. Okay, so that is the solution. So B, show that star holds for every f in L1 of 0 infinity. So this is really the Riemann-Lebesgue lemma which we want to show. So by A, star holds for all step functions. What is a step function? It is a simple function where each element chi ei is a form of an interval, okay, in one dimension. That's a step function. And therefore, now we have also seen step functions are dense in L1. Okay, and let us assume that mod h is less than or equal to m, which is because it's a bounded function. Okay, so given epsilon positive, there exists a g in g step function, norm of f minus g in L1 less than epsilon. Therefore, mod integral 0 infinity f t h omega t dm1t is less than or equal to mod integral 0 infinity ft minus gt h omega t dm1t plus integral 0 infinity modulus gt h omega t dm1t. Now we know that this goes to 0 as omega tends to infinity. Now this one is less than or equal to m, which is the mod h is less than or equal to m integral 0 infinity mod f minus g dm1t, and that is just norm f minus g L1. Okay, and then this is less than m epsilon. So you can find g as close as possible, so that this can be made as close as you want, and once you have g, you can find omega large enough such that this is as small as possible. So this implies star. C. So f in L1 of AB contained in 0 infinity. Limit n tending to infinity integral over AB of ft cos nt dm1t equals limit n tending to infinity integral AB ft sin nt dm1t, and that is, they are both equal to 0. So solution: extend f by 0 outside AB. So let f tilde be the 2f tilde. Then f tilde belongs to L1 of 0 infinity. Now if I take ht equals cos t, then you get 1 by c mod 1 by c integral 0 to c cos t dt. This is less than or equal to 1 by c. Then cosine is sine, so sine c minus sine 0 is just that. So sine c, which is less than or equal to 1 by c and goes to 0 as c tends to infinity. Similarly, if you take ht equal to sin t, you have, so 1 by c integral 0 to c sin t dt. I am using dt because you are dealing with continuous functions, finite interval, therefore Riemann and Lebeg integrals are the same. I am not writing dm1 because of that reason. Okay, and this is equal to 1 minus cos c by c, which is equal to 2 sine square c by 2 by c, and therefore that's less than 2 by c, which goes to 0 as c tends to infinity. Okay, so therefore this implies that integral f tilde t 0 infinity, okay, cos nt dm1t tends to 0 as n tends to infinity. We are taking omega equals n, and integral 0 infinity f tilde t sin nt dm1t also goes to 0 as n tends to infinity, which proves the thing, because and then f tilde is nothing but chi of AB times f. Okay, so therefore the result follows. 4. A. Consider the trigonometric series A0 by 2 plus sigma n equals 1 to infinity an cos nt plus bn sin nt. This looks like the Fourier series, but this generally only a trigonometric series. There is no function attached to it. Okay, so write it in the form A0 by 2 plus sigma n equals 1 to infinity dn cos nt minus phi n. So this is called the amplitude phase form. Amplitude is dn, phase is phi n. Okay, what is the relationship between an bn and dn phi n? So this is of course trivial. Okay, so you just write an cos nt, sorry, an equals dn cos phi n and bn equals dn sin phi n. So that means dn is the square root of an square plus bn square and phi n is tan inverse of dn by an. Okay, so then this is well defined. So this gives you the thing, and then if you substitute, then you get a0 by 2 plus sigma n equals 1 to infinity of an is dn cos phi n cos nt plus sin phi n sin nt which is nothing but a0 by 2 plus sigma n equals 1 to infinity dn cos nt minus phi n. Cos A minus B formula is all that we have used. Okay, so now is a very interesting result. So this is called the Cantor-Lebesgue theorem. If the trigonometric series above converges over a set E in R such that the measure of E is positive, show that an bn tend to 0 as n tends to infinity. So if you look at the trigonometric series, so you have an cos nt plus bn sin nt. If the series converges, all you can say is an cos nt goes to 0 and bn sin nt goes to 0. Okay, that's all that you can say from this. But we want to show that an goes to 0 and bn goes to 0 individually. Okay, so this is different from numerical series where the general term goes to 0. Is here it doesn't fully imply that. Okay, so with solution without loss of generality, we can assume 0 less than m1e is strictly less than infinity. It's finite because you take a smaller set of finite measures. You have a set of positive measures where the convergence takes place. So you take a finite measure subset of it. So there's no loss of generality of that. So the series converges implies the general term goes to 0. So dn cos nt minus phi n tends to 0 as n tends to infinity for every t in E. Okay, so claim dn tends to 0, which will of course imply that an tends to 0, bn tends to 0. So it's enough to prove this claim. So assume the contrary, then there exists a subsequence nk and epsilon positive such that dnk is greater than or equal to epsilon, strictly positive. And this will then imply that cos nkt minus phi nk goes to 0 for every t in E. So measure of E is less than plus 1 implies cos square nkt minus phi nk is integrable. So modulus of this is less than or equal to 1 and therefore this is integrable. Also, it is less than 1, which is also integrable. Therefore, by the dominated convergence theorem, you have integral over E cos square nkt minus phi nk dm1t goes to 0. That is integral over E 1 plus cos 2 times nkt minus phi nk by 2 dm1t goes to 0. Now, integral over E cos 2 times nkt minus phi nk dm1t, what is it equal to? It is cos 2 times phi nk integral chi e over r cos 2 nkt dm1t. And integral, okay, plus, sin 2 phi nk integral over r chi e sin 2 nkt dm1t. But chi e belongs to L1 of R, since you have that M1 of E is finite. Okay, and previous result, that is problem 3C, okay, also applies to R, minus infinity 0 and hence to R. You just have to do everything with the minus sign and you will get the same whatever you did in that exercise. So therefore, you have that integral chi e cos nt dm1t over r tends to 0 and integral over r chi e sin 2nk dm1t also goes to 0. So both these terms go to 0, that means the cosine, integral of the cosine goes to 0, and therefore we have that integral over e of cos square nk t minus phi nk dm1t goes to integral over e 1/2 dm1t, which is equal to 1/2 of m1e, which is strictly positive. Okay, and but so this is a contradiction because we saw that it goes to 0. So we saw that it goes to 0, so contradicts star. And therefore this implies that dn goes to 0 and that implies that an and bn go to 0. So this is a very nice application of the Riemann-Lebesgue lemma, and so we have applied essentially the thing depended on step functions being dense in L1. So we will continue with the exercises next time.